I think we'll go ahead and get started with our next meeting on industrial applications of benchtop NMR. First, we'll have a little note from our sponsor.
Good morning, everyone. Good afternoon, good evening, wherever you may be. Once again, great subject material today. I've got a very, very good panel lined up and looking forward to it. MR Resources and Q1 Instruments are very happy to be bringing the Abbvie meetings to you. And MR Resources, of course, have been around for over 35 years at this point, and providing reconditioned NMR systems, magnets, consoles, probes, service contracts, quench magnet recovery, and certainly moving and relocation. In fact, they've got a very impressive inventory of reconditioned instruments on hand, and three in particular, very spectacular offering, all Brooker Avance 3, 600, 700s, and they've even got a 950 in inventory at this point, all with cryo probes. Certainly check them out, get in touch if any of these interest you. And Q1 Instruments, a little bit newer to the industry, but Eric, could you give us some brief information on Q1, please?
Okay, so welcome everyone. I want to introduce Travis today, Travis Gregar from 3M. He's going to lead the part 2 of industrial application of benchtop NMR. Before that, I want to announce what is coming down the pike in Abbvie workshops. On December 1st, we have Murali Nagarajan from Rutgers doing an introductory bio-NMR panel discussion with Professor Ranjit Ghosh and Professor Andrew Newcomb. And in January, that concludes our 2022 series. Then we kickstart 2023 in January, date to be decided, probably typically the fourth Thursday of the month. Ishwan Pelser from Princeton University will lead a panel discussion on Fourier transform on time domain NMR or complementary for metabolomics. And the panel is to be decided at this point. Then following that in February, Gennady Kirish from Merck is going to lead a discussion on water suppression methods. Again, the date and the panel members will be announced very soon. March is still in the works, and April will probably enter into the ENC user conference, and so we will not have an Abbvie workshop in April. So those are the three or four topics that are coming down the pike. Watch your email for the announcements. With that, I will pass it to Travis, or is Don ready to? Don, are you? Is your microphone set up properly?
He's killed his video. We'll just go ahead and pass it over to Travis.
Okay, so I'll pass to Travis to take over the panel discussion. Travis.
Excellent. Thank you, Krish, very much, and welcome everyone. This is a part 2 of Benchtop NMR Symposium. Month before last, we had a very good discussion that is posted on the Abbvie NMR website. If you missed it, I strongly suggest that you watch that. Some very different applications of benchtop NMR that led to some very good discussion. Today's panelists between Greg, Adam, Mark, and Chris should also give us a very good discussion as well. I think benchtop NMR is becoming just even more and more common, and I think the more that we can demonstrate how people are implementing NMR in our own laboratories, hands-on, being practical, we can start to make more inroads into industrial applications and show the utility, so we don't have to keep getting pushed over by LC or GC in a lot of applications. So with that, I was going to have Greg Webster from Abbvie. Greg is going to be talking about using DOE to optimize selectivity in NMR relaxation studies.
All right, thank you, everyone. My name is Greg Webster. I'm from Abbvie outside of Chicago, Illinois, United States. And we've been working with Benchtop NMR with NMR relaxation, TD-NMR. We use I'm not an NMR person, so be gentle. I'm an analytical chemist who uses NMR when the toolbox tells me it's the way to go. So we've been using TD-NMR to look at protein identity testing, and basically we've been focusing on the T2, but we also look at the T1 value as we're going. We got it started with this work based on the handheld version from waveguide, but we've had some other applications that we've needed to look at TD-NMR with, and we've gone to a benchtop instrument that we have on site. And so one of the questions is that for someone like me who's not an NMR expert is, where do I go? How do I start? So we had these TD-NMR parameters. These are the default parameters from waveguide for T1 and T2. And we used them based on, as we did an extra T2 parameters based on our NMR person, but we looked at some differences between albumin, and the goal of this study was, could we tell the difference between the source of albumin? So if we had BSA and someone gave us human albumin, porcine albumin, egg white albumin, anything we could find from Sigma, could we distinguish it? And as you can see a little bit of just differentiation from the T1 result, and then T2 is where we expected to see greater differentiation. So the question is, for someone like me, how do I optimize the experiment? And not being an expert in NMR, I defaulted to design of experiments to help me look at the parameters. And so the goal for this study is, how can we maximize the separation of those T2 values so that we could have selectivity for our experiment? So taking the parameters from SpinSolve, we needed to see, first of all, what parameters are critical. We kind of had an idea talking to the NMR people, but we wanted to go through this in a systematic manner. So we took the midpoint of their suggestions and actually took the values above and below to do an initial screen for the DOE, which we did in Minitab. And so using a Plackett Bergman design, we basically did a 15 run design for the factorial, and we took the values for BSA, human, egg, and porcine T2 for each of these different conditions on the benchtop NMR. Now, of course, since we're looking for the maximize the selectivity, we didn't want to give the actual value to the DOA software. What we did is we gave the differences between the T2s for the NMR software, or for the DOE software. And in design, we said, maximize those differences so that we would enhance our selectivity. And doing our parameter factorial, we could see that the CPMG echo time and the final echo time were probably the only parameters that were critical to the experiment. But we did have some took the software and said, okay, maximize the experiment, and then we could get these current settings of for each of the parameters, saying these are the optimized parameters for the experiment. Now, our statistician said we had some curvature in our data, that we should look for a response factor instead of parameters and look at that further. And this time we did that just looking at the CPM echo and the final echo times, and then using the optimized conditions for the other values. And as we could see in this critical response factor is pretty much still the CPMG that is the critical factor on the Magritech waveguide, Magritech system for relaxation studies. And so we could take these optimized parameters and maximize them, and said that a 1 second CPMG is probably the optimized value we wanted to go. And the final, it wouldn't let us just do one parameter, so we did the final runtime too, and basically as long a time as we could give it would give us our optimum parameters. So looking at this data, just looking at a T1 and T2, we could see that we could differentiate the the albumins pretty readily for the experiment. Now we're using albumin here from Sigma so that we have intellectual freedom, intellectual property freedom for doing on this. That whole project was for another set of proteins that we are working on, and we also didn't have a lot of lots to investigate. So what the experiments, when we have the error bars, when we show these things, basically I was able to get several lots of the BSA material, and I applied that variability to all the other data points. So it's kind of an idealized selectivity. But the question is, could we do better and re-optimize our DOE to use all the different samples that we are going forward? And actually, because T2 is sensitive to temperature, we wanted to add a delay to the sample so that we were sure that the samples were coming to equilibration. One of the nice things about the Magritech is that the magnet operates at 26 degrees above our room temperature, so that we could use that to have a constant temperature in our TDNR NMR relaxation experiment. So when we did that, we repeated the response factor experiments again, looking at all the different factors that could go on based on the selectivity of all the different parameters, not just a few of them. And we still could say that that the CPMG was probably at where we were the most critical. We did the optimization based on our full set of data, and this time we added a DOE for the T1 parameters. Same way, taking the optimized conditions, going high and below, and also doing a design of experiments for both the T2 and the T1. And then we could have our critical parameters as well. What we found in our design of experiments is that we did not have critical parameters to watch for our T1 experimentation. So we maximized the experiments for both of them. And as you can see on this one, our T1, T2, the data isn't really as nice. We added more samples to it, and it kind of bunched up a little bit on us. So the question is, what happened? And what happened is a little foreshadowing, is our maximum inversion time is too low. And that illustrates one of the problems we'll see with just using design of experiments without asking your NMR people to look at the data as well, is that we can get to some areas where we're minimizing the variances, but we're getting into a dangerous part of NMR. So we always have to, just as in our HPLC design of experiments, we have to look at the data a little bit more closely than just taking the default values. So we did our surface DOEs and our optimizations here, and I'm moving ahead because I'm trying to go. I lost my spot. But what it was is that when we started doing the T1, our immersion time was optimized around 50 milliseconds. And as you can see, that peak is sitting on the negatives going downward. And if I did 5 milliseconds, the peak is going upwards. So basically, when we were optimizing the experiment at a point where the pulse was not allowing the T1 value to recover. So we had to go back and re-optimize our experiments. Our design of experiments told us to go in one direction, but didn't really care about the NMR aspect of it. So knowing that we needed a longer pulse to get a full recovery of the signal, then we re-optimized the values after that. And so our Magritech system, we could get away with a short number of scans. Our acquisition time was 6.4 seconds. Our repetition time was 35 seconds. This time we used a CPM of 2 because it broadened out a little bit. We added more samples and a number of steps that are going through there. And our T1 values weren't all that really critical for what we're doing. But as you can see on a benchtop NMR, for looking at the data, we see a little bit of variability going through here, but our system precision, which looking at 6 different weights of the BSA lot, was 0.2%. And our method precision, looking at the same sample, was I'm sorry, our system precision was 0.2, looking running 10 samples over 6 times in a row was 0.2. Our method precision, looking at 6 different weights, was less than 1%. So the important thing here, as kind of what Trevor was alluding to, our NMR was actually operating just as what we would expect our HPLC to be running, right? We on our HPLC, some of the older ones we want 1%, some of the newer ones we want less than the 2% if we can, 0.2% if we can get away with it. So the NMR was operating every bit as tight as an HPLC here, which is good to see. The variability we're seeing is actually from the proteins. And then for the T1, we can see that it was even tighter RSDs, and that we were seeing very good reproducibility in the instrument. And then looking at that with using our optimized conditions, and this time taking into consideration for that the T1 signal would recover, this is the data that we would see. And the reality is that the T1, the TD-NMR, the NMR relaxation isn't going to separate every protein. But in this particular study, and on our study for internal Abbvie, we had a bovine source and a porcine source, and the TD-NMR or the NMR relaxation could easily differentiate them as an identity test, which was much more rapid than trying to do some of the HPLC. What typically doesn't show that big a difference in these materials, and so we have to do some more derivatization or further testing to do the chromatography or the mass spec aspect of it. So as a quick ID test, we could actually use NMR. So my observations for the BSA that we could distinguish several of the sources, but not all the sources. Using T1 really didn't, for this particular investigation, help us all that much. It's good to have it because we can run it, doesn't take that much longer, it gives us a little bit of differentiation, but T2 is critical in our experiments. What we also learned is that optimizing these conditions for using a design of experiments was great for this particular samples, but if I wanted to throw other proteins, antibodies and things that we're interested in, we actually have to look for new optimized parameters. So it wasn't that they're not that universal for what we're looking for. But TD-NMR and NMR relaxation on the benchtop did show excellent discrimination for protein source identification. T2 is much more discriminating than T1. T1 doesn't contribute that much. We still need to do some extra work seeing how we complement this with size exclusion chromatography. And all these experiments were proof of concepts. So we need some larger data sets to understand what is going on. One of the challenges we have here, we're working with proteins. So proteins are a little bit more variable in themselves than what we'd see from our small molecule work. And so we have to look at the variability of sample and how it plays into this. But TD-NMR NMR relaxation seems to be a very interesting tool to do some rapid identification studies. And whether you do it on a dedicated TD-NMR experiment or on the benchtop NMR, we're seeing the data is correlating quite nicely. So thank you to our statistician and Cassie Yang, our NMR expert, for some of our discussions in TD-NMR. Do I have any questions or?
Great. Thank you very much, Greg. Very nice talk. Thank you. Jose has a question. You want to ask that, Jose?
Yeah, sure. No, just quick question. I saw that the flips diagram appeared in one of the slides, and I was just wondering if you guys use it, if it is implemented on the Magritech, or if it's something that, if it comes with the box or if you have to implement it yourself.
We just use it to explain the data, why was going negative, and we used it to understand it wasn't something we were doing wrong. We just it illustrated for us that just taking a design of experiments blindly is going to get you into trouble. So that there are reasons why some of these parameters give you some funky data, and for us, we used it to show that hey, our T1 value is way too small. We should be working in a different range for proteins. And that I'm sure the NMR experts, that are on the phone would know this intuitively, but as someone who's just done more HPLC than anything else in the last 30 years, I use design of experiments to help optimize. I got into trouble just using that. So it's always important to bounce this off that. And so the illustrations really show that don't just follow your design of experiments blindly. You got to look at the data and look at the parameters, and it will give you some bad parameters if you don't look at the data, because it's just looking for the minimization of the variances. Mm-hmm. So it was doing what it was told to do, but it was in a bad region. Once we moved it out of that region, the design of experiments worked great.
Great.
Thanks, guys.
Thank you, Jose. Let's answer one more question. We've got quite a few in the chat here. Let's see. Brian kind of asked the same question I was thinking about. Is how Brian, you want to ask your question?
Yeah, sure. Good talk, Greg. I was wondering about solution conditions and sample prep. How important are they in terms of the T1, T2?
Well, we found with our antibody work, obviously concentration is going to mess us up big time. So for all this particular work, I had prepped all the albumins to be at 5 milligram per mil in a buffer solution, just a off the shelf pH 7 buffer. So, but yes, if we change our matrix, we change our concentrations, we could get into trouble for that. We've seen that some of the antibodies that are different concentrations are going to have some different values. We see that actually as an advantage though, because our whole idea was looking for a receipt test for GMP. And if I was expecting to get 5 milligram per mil of a particular protein and I got 15, I would want that test to fail. So the key with TDNMR for us, it's a great, cool tool looking for the right application. And we've been throwing a lot of the wrong applications at it. But it's got a lot. It's a pretty powerful technique. It's pretty amazing. You get this selectivity just watching water relax. But we have to be careful and use the experiment for the right way and not just try to throw it at everything.
Thank you, Greg. In the interest of time, Greg, could you, can you answer some of the additional questions in the chat?
I'll look into them. Yes.
Great. Thank you. Thank you very much, Greg. Very nice talk. At this time, we're going to go on to Adam Sutton, who's from Merck, where he's going to be talking about quantification of vaccine components by benchtop NMR. Take it away, Adam.
Okay, hi everyone. So I've been working in the vaccine analytical research and development department at Merck for 2 years now. And so like Greg, we're not like an instrument focused group where we look at various tools and we always have to screen different things to see what's the best tool to use for characterizing our vaccines, which are very complex mixtures that exist in many different types. And so I'll just introduce you to some of the different types of vaccines that we have at Merck. So these are ones that are already commercially made, but we also work on all the new vaccines that are always coming up through our pipeline. And not only do they exist as like injectable vaccines, we also have oral dosed vaccines like the rotavirus one here. And they all come in different forms. So here we have vaccines for pneumonia, which involve polysaccharides, sometimes conjugated together with proteins. We have other vaccines which are protein-based and form virus-like particles where the proteins self-assemble into particle structures, which occurs here in these hepatitis B and our human papillomavirus vaccines. And then we also have live attenuated virus vectors for vaccines where a virus has been modified somehow to provide an immune response against a particular disease. And then not only do we have there are other vaccines that exist in the world as well, like everyone knows about mRNA vaccines that are used for treating COVID now. And so vaccines are a very complex mixture that come in many different forms. And so we need to have various different kinds of technology to help characterize and not only the final products, but as the vaccine is being developed and being produced, we need different tools to study each step of that process. And so vaccines tend to be broken down into 3 major different sections. One will be the main component, which is providing the immune response. So that could be the polysaccharide, the virus-like particle, or some kind of virus, or the mRNA. And really the only thing that you can see that these have in common is the fact that they're all really large molecules. Otherwise, chemically, they're all very different. And so that makes it very challenging to study them independently. There's also other components there. So we need excipients to help keep the vaccine stable. These can be things like just buffers to keep the pH constant, salt for the ionic strength, stabilizers like polysorbates, which just prevent things sticking to the glass or can act as a surfactant to help everything stick together. And then lastly, we'll have things like adjuvants, which are components designed there to improve the immune response from these particular vaccine components. And adjuvants are a very broad category of compounds that many different examples exist out there in commercial products. One common one is alum, which is just aluminium salts, which are suspended in the vaccine. Lipid emulsions are a very common adjuvant as well. Then things like oligonucleotides as well. are also used in vaccines to help improve that immune response. So you can see here that all the vaccines are very broad in terms of their composition, and each one requires its own unique tools to kind of look at what's there. And why we choose benchtop NMR as something that we investigate is because typically these active components are problematic for a lot of our analytical tools because they're so large. But the fact that they're so large and diverse in their chemistry, they're often not seen in our benchtop NMR spectrometers. And so that allows us to focus more on some of these other high concentration components, such as the excipients or the adjuvants. So some of our general ideas for that we've been investigating the benchtop NMR for. The first one is kind of like, they're very similar to what Greg was saying in that we're competing with liquid and gas chromatography methods. So just using benchtop NMR as a quantitative tool to measure different components and then comparing them, like seeing if they can be more efficient than our chromatography methods that are typically being used in our area. We also like the idea of using the relaxation measurements as a unique identification for our vaccines or the vaccine components. We also think that benchtop NMR has a good role in the pharmaceutical industry for identification and quantification of raw materials. So sometimes our raw materials don't only need to be identified, but they also need to be quantified. And often that involves doing chromatography methods, which tend to make just obtaining the material quite difficult. And so we think that benchtop NMR can be a much more efficient way to do that. And lastly is using benchtop NMR as a process analytical technology. So being able to monitor reactions happening in real time. But for the sake of time, I'm mainly just focusing on the first two areas here that we think are good applications for benchtop NMR to be investigated in. So the first one here is looking at excipients. So very common excipient mixtures that exist in all kinds of vaccines is just some kind of buffer with a polysorbate. So here we have histidine with PS20, which here they just work to help keep the mixture stable and not sticking to the glass. And so we've tried this with various vaccines, and we always get the same kind of spectrum where you won't see the major component, whether it be like proteins, polysaccharides, all those big things. They don't appear. We just get very clear signals that relate to the histidine and the polysorbate in question. And what we like about benchtop NMR is that it's very convenient because here we have to screen so many different tools. When something is very convenient and easy just to try, it's likely that we're going to go and try the benchtop NMR first, just because it's easy to use and see if it goes okay. And so for these samples, we're all doing our quantification with an external standard. So then we're just taking the whatever sample we have, putting it directly into the tube and then measuring, and then we get this spectrum here. So it's very convenient. And everything we present is without any deuterated solvents. We very rarely use deuterated solvents just because it's too difficult to reconstitute something in there. You really lose that convenience. And so, yeah, you don't see those active components. And often our things have a lot of salt in them as well. And we don't really get any problems with salt interferences, which sometimes our high field colleagues tend to complain about. So for the purpose of measuring these kind of excipients, we're just using a pre-saturation water suppression technique, no deuterated solvents with our external calibration to quantitate the polysorbate or the histidine. And sometimes precision, like how much precision we need varies depending on like what data we kind of need there. So we have like two possible situations where we can measure for longer to improve our signal to noise ratio and lower our RSD. So if we measured for 17 minutes, we can go down to 2% in terms of quantifying these components. But if we just wanted to do something much faster, we don't really care about how precise it is, but we can do a 10% RSD measurement in just 4.5 minutes. So that makes it very convenient. And so we have to compare this to our chromatography methods at the moment, just to see how accurate is the NMR and how reproducible it is. Because when you're trying to do these kind of measurements, not only does it have to be convenient, it needs to be very easy for non-NMR experts to use it. Because at the moment, typically if we talk to our colleagues, they'll say NMR is very complicated. So we have to do a lot of effort to show how benchtop NMR things cannot be they're always complicated. So we have 3 different people. 2 of them were not like NMR experts in any way, who've never used the spectrometer ever. And then we can get RSTs less than 5% on there. And then we're getting values very close to what we get with our liquid chromatography measurements. And so with having the ability to kind of do this in an efficient way that's easy for anyone to do, the software becomes a very important aspect for us. So we use a Magritech 60 megahertz instrument, and using the QNMR software that they have has been really handy for us. And so we did our own kind of experiment to see how easy is the software to use. So with these kind of measurements that we had done before, we got an intern to come work in our lab for 3 months, and then got them to just make other QNMR methods using internal and external standards, and to see if we could train them in just like small amount from what we knew, how easy would it be for someone who's not trained in NMR to develop these methods. And we thought it was quite successful. By the end of 3 months, our intern was able to train other people who had never used NMR before on how to make these methods quite confidently. And so looking at their results here, comparing NMR to chromatography-based methods, you can see that for the polysorbate, we're getting less than 5% difference between our LC and NMR measurements. And then looking at that histidine, it's more like a less than 8%, less than 10 when we compare. And so this is someone learning how to use the Benchtop NMR or like with very little instruction from us, and then being able to do it. And so we were very impressed with how easy the instrument is to use, and the software as well. Another application we've been looking at is just measuring solvent compositions. So typically you would use something like gas chromatography to look at solvents, but to set up a GC instrument takes some time, preparing all the standards, making your calibration curve. So we've been looking at how we can use the Benchtop NMR to do it in a much more faster way. So some of the samples that we get here in a purification step involve changing the solvents, so the ethanol, isopropanol, acetate, and phenol concentrations. And they'll do experiments to optimize these ratios to optimize the purification process to maximize yields. And so they need to keep track of what the concentration of all of these solvents are. And so if we take a sample, we just would directly mix it with an internal standard in this case, and then put it in the NMR tube. And again, we get a very nice spectrum where the active components that they're trying to purify, they're not visible at all, just because they're so large and they exist in such a small concentration. While the solvent components, which are in like really high concentrations, like 30%, 5%, they're the main things that we see. And since they're in such high concentration, you just need like single scan measurements to detect them. And so in 30 seconds, we're able to identify all the components there, the isopropanol, phenol, and acetate, and quantitate them very easily with the internal standard. And so again, we have to compare to our chromatography competition that this is a typical way to do it. And we were very happy with seeing that the NMR and GC values are very close to each other when we're doing spike recovery measurements. So the accuracy of the NMR versus GC seems very similar. It can sometimes actually look like the NMR is performing more accurately than the GC, but I think that's just because we weren't looking at that many samples for the spike recovery measurement. When we did a much longer comparison, so looking at multiple samples between NMR and GC, and so the NMR being measured by multiple operators, we can see that the trend and how similar the values are is relatively consistent. There was only the occasional outlier where the GC and NMR would be very different to each other. And we also have to compare to the estimated value. So typically when they're putting these solvents into their purification system, they'll use mass calculations to confirm how much they're putting in, but that doesn't give you the individual composition, which is where they come in to get the GC or NMR measurements. And typically you can kind of see that samples tend to get submitted in batches of say 4 or 5, something like that. And so what we could see is just the time that it takes to do this. GC is 9 hours for 4, well, NMR is in 5 minutes. Another application that I'll talk about is looking at alum, which is the alum adjuvant in our vaccines. So alum is these aluminium salts which are suspended, but it's not usually a stable suspension. They often sediment, and so knowing the sedimentation rate and what kind of sedimentation state they're in is important for the vaccines. And so there's a lot of things in the literature about studying alum sedimentation and aggregation and things like that. And so we look at them in a similar way to what Greg was talking about with the proteins using water proton NMR. So just doing T2 of the water signal there. And since we think like T2 is handy for vaccines because the larger components in the vaccine, so whether it's the alum or the active components there, which are very large, will contribute the most to changing the T2 of the water. And so that allows us to look in terms of having like a unique identifier for the vaccines, as well as potentially quantifying specific components. So we've been trying to investigate that. And so we have like our 60 megahertz Magritech system. And so one thing that was particularly important for us was that since the alum sediments, you need something that can measure very quickly. If you measure the T2 too slowly, then you'll get a bias in the fitting just because the things are settling down. Nothing to do with the actual like alum itself. And so to try and look at quantitation of the alum, we looked at calibration curves. And then we noticed that if we take the same alum and then we suspend it in different mixtures, we'll get different calibration curves, which supported our idea that it could potentially provide some unique identification for the vaccines. But that also made it problematic in terms of the quantification. We knew that we needed to make sure that we would do the quantification with external calibration where the alum existed in the exact same formulation as the background. And so we had some like spike recovery experiments there where we added to it just a vaccine formulation, a specific amount of alum. And if we were to just use alum in regular water, then our values would not be correct for what we had put in. But when we match the formulation buffer for the standards of the alum, then we're getting very accurate results. So we think that the water proton NMR, if you having a consistent product, can be very handy for checking the alum concentration that's present in the vaccine, or just in the manufacturing steps as you go through. And then we thought we could take this further to study the sedimentation. So we're looking at everything in NMR tubes. And then since we have to measure quickly, otherwise the alum sediments too fast for you to detect it. We thought if we just do these measurements over time, then we should be able to track the sedimentation of the alum down the NMR tube. And so we looked at 3 different vaccine mixtures, and we were surprised to notice that the sedimentation profile varied very differently with the vaccines that we were studying. Some were sedimenting in like very fast here. This one is in less than 12 minutes, while in a very linear fashion, while a different vaccine was sedimenting in a much more exponential decay over a very long period of time. In terms of like alum sedimentation, that's very long. While in another vaccine again, didn't have this like consistent sedimentation. It seems to have different properties in terms of the profile. And so we didn't really look too much into the rates of the sedimentation, but just using this sedimentation profile as different ways to kind of identify unique fingerprints for our vaccines. Like, can we identify what's there? To conclude, so for us, the Benchtop NMR is a very convenient tool, and we don't think that it's something that should be limited to NMR experts. And from our experience, it's very similar in accuracy and precision to chromatography methods, but it's much greener and faster in many cases. And so that's where we continue to push Benchtop NMR as an alternative for some chromatography methods. And it's very versatile, but only for us, like looking at the high concentration components. Because some of the difficulties we have is if we wanted to look at something that's not in high concentration, then we struggle a lot to get enough sensitivity and to avoid signal overlap. And just like one kind of like problem statement that I'd like to put out there, for us, one problem that we often run into is the lack of being able to baseline certain peaks. So here, this is a very common spectrum that we kind of get, where we'll have two peaks of interest, these ones here with the blue dot, where they're almost resolved, but not completely. And the automatic baselining doesn't bring those peaks straight down because they're not completely resolved. And so we want to integrate those, but in the SpinSolve software from Agritech, since we don't have the ability to kind of set our own local baseline, then we have an over integration. So we have integration error there. And we've confirmed this with if we run this in a high field spectrometer where it's completely resolved, or if I put it into a different software, do a baseline correction locally, then we get perfect measurements. And so for us, this ability to do baselines is the biggest, the most frequent problem I'd say that we have, because we're always running into spectra like this, where it's oh, we're just a little bit unresolved, but if we baseline it, it would be fine for our quantification. So I'd love to hear people's options for improving that, or if other people are also running into this same issue. And then I'll leave it there with some acknowledgements from the different people at Merck that contribute to our Benchtop NMR studies, and Magritech, who is always very supportive for helping us and giving us lots of software support.
Excellent. Thank you, Adam. Very, very nice talk. There's quite a few questions in the chat. Why don't we ask a few of them, and then you can follow up with any questions that were not answered. Victor, do you mind asking your question?
Yeah, let me just unmute. Yeah, so you said that, or I guess my question is just, do you suppress the signals from the active ingredient? I know you say it's low concentration, but I wonder if it still has an influence on the integration.
Only if it's really high concentrations have we ever seen it even appear. When it's in these low amounts, just I think the software will just assume that it's part of the noise in the baseline and subtract it.
Okay.
But we know that T2 filters are coming more available, and that's our way. When we once had seen it did give a signal, T2 filters was our way to go to avoid that.
Great. All right, thanks, Adam. Great talk.
Excellent. Does that answer your question, Goncalo? Do you want to tag on to that?
Kind of. So in these magnets, especially if you have aqueous samples, your water peak can easily max out your detector. So you see an overall spectral reduction of all intensities and of all features, right? So you're saying that you're using, the downside is that if you want to suppress that water peak, then you need to use a water suppression pulse, right? So what is the trade-off between that water suppression and just overwhelming your detector and everything gets dumped down? So have you managed to understand the differences between using water suppression method or without water suppression method? And if those methods that you have in Magritech, do they come standard with the box, or is it something that you guys developed in-house to optimize and maximize that water suppression?
Okay, so yeah, we just use the standard things that Magritech gives us. Convenient is the word I like to put all the time. We don't do anything that's inconvenient for us to do. So we just use the preset option. For samples that don't have deuterated solvent, I think we always just try preset. We'll run a normal one just to compare, but I would say typically the other signals, if we compared, don't look like they're reduced in comparison to our preset one very often. But we've never really quantitated those samples. We always just quantitate with the preset, because it's just a matter of going click preset instead of click 1D. So it's not really a hassle for us to do the preset option. We recently got doing wet suppression, and that's something we're just investigating now, is about how much better are those water suppression techniques. And you'll hear from another Merck person soon about in another Ivan meeting about the different water suppression options.
Nice, thank you.
Excellent. Thank you. Thank you. Thank you very much, Adam. Very, very nice talk. As you, in order to keep things moving forward, Adam, would you mind answering some of the questions in the chat?
Yep, sure. I'll give you a go.
And then if, as time allows towards the end of the meeting, maybe we can circle back on that. I want to introduce Chris Thomas, a speaker near and dear to my heart. I've known Chris for, gosh, 22 years now, as a both as a colleague, both here in the same building that I am at 3M. And now he is a senior staff scientist or senior division scientist down at our Decatur, Alabama plant, where he's going to talk about lessons from a non-NMR point of view. So I'll let you take it from there, Chris.
So yeah, I'm going to follow in the footsteps of the previous two speakers. I'm not an NMR person, so just want to give some of the lessons we've learned as we've journeyed towards implementing benchtop NMR at 3M. And I live in a factory, so really practical kind of stuff going on here. So the background, I'm a highly experienced analytical chemist, but I speak zero NMR. I speak enough to know and understand when somebody says, here's the difference in composition. Okay, I got it. But as far as actually, digging into the details of NMR, I am not that person. So, and we're also in a plant environment, so we're not doing rocket science here. We're usually trying to solve everyday practical problems, and definitely something benchtop is one of those tools that we're looking at. Looking to add to our toolbox and our Swiss Army knife here of capabilities, so it's not just FTIR or Raman or something like that, to really to look for something else. How do we start? Really my approach is right here, just jump in. Like that's, I think, what we did. The train's moving 100 miles an hour, just jump on. The objective is to really complement, like I said, with our existing tools to get more direct chemical composition for small molecules, mixtures, and polymers. And our challenges, I'll go through, I won't dwell on them here, but definitely some challenges when I tried to learn the field of NMR. So first of all is selecting it and justifying it. This is something that's not new. We've been working on this since 2013. John Batiste in our corporate analytical group worked with us back, almost 10 years ago, trying to look at this technology. It wasn't the right time, and we just didn't have the justification, but we kept doing potential samples, kept collecting potential sample sets for quite a while and kind of doing them in parallel, high field, benchtop, and just see, is this something that will eventually give us useful information? Definitely over time, we figured out that, yeah, I think this is something we can, even for a novice person, we can get some information out of this. So we tried, when we bought it, we tried to get as much as we could. We got the top of the line system at the time, an auto sampler, all that kind of stuff. And by the way, this is not an endorsement, but it's a great system for us. So here's the start of our gaps. I'm not an NMR person. I have never done NMR before. So to me, it's a black box. I don't like black boxes. I really want to understand what's going on. How is the signal generated? What's going on physically? I speak organic chemistry as like a 11th grade Spanish class. I'm sort of learning, I know organic chemistry if I could sit down and do it, but I'm not going to, speak all the detailed language. So I had a lot of catching up to do in this regards. Instrument components, operation, how to interpret the signals, all the different experiment modes, etc. There's a lot to dive into for a novice. And, sometimes you look at some of the courses that are out there and they kind of dive right into a lot of the more detailed stuff. So I tried to find, I'll shamefully admit it, that I found some YouTube NMR videos to help me kind of at least figure out how to spell it. And then some books that Travis had suggested that I start digging into have been very helpful to get me on this path. Supplies and preps, various practical stuff, but which solvents do I need? By the way, to get a solvent in a plant, it's a lot of work. So we had to go through a lot of approvals. Which ones do we need, etc. Even with, if you say chloroform, okay, which one? There's like 30 different grades of chloroform for NMR. Which one? It's just practical stuff, right? Spinners, we had some compatibility issues that Magritech helped us through with using TFA with these spinners. We had evaporation from the typical tubes, the caps on these tubes. We found some that gave us some advantages of slowing down the evaporation, how to prep the samples. we have TFA as one, concern. So what do we use to prep the samples? We figured out ways to do that. How much sample do we use? Typically 25 milligrams per mil. Well, what if we tried a much higher concentration? And yes, that actually worked. I'll show some examples. Waste protocols, waste streams, we're going to dispose of this stuff. Where do we put it? Safety concerns, we're looking even into robotic handling of sample prep if we do go to a QC type environment where we reduce exposure and improve repeatability. Instrument setup is kind of intimidating. You got all these. I'll give you guys the jackpot prize for the amount of abbreviations for all these different kinds of things. What do they all do, and how do you optimize those? So we've also gone down that DOE approach, looking at things like phase angle, number of repetitions, simple stuff, concentrations, scan times, etc. Yeah, it's kind of overwhelming. So just take it one at a time and, really figure. It's been so great to have Travis and Eric in our corporate lab as teachers, and they say, we'll try this because here's why it might work. And yeah, we go do the experiments here. So it's great to have someone as a buddy to help us through a lot of this stuff. Data analysis, somebody mentioned earlier, a lot of the peaks are kind of maybe not baseline resolved. So we've done some work. I saw Krish is on the line. Krish helped us look at some software that can sort of deconvolute some of those. Otherwise, this peak right here down on the bottom here where my cursor is, you can see this little peak right here is the one we're interested in, but it's swallowed up by this larger peak. And we've shown feasibility, and we're pursuing looking at this in our lab to make the data analysis a little more straightforward. There's some examples of doing this. We have, and I can't talk about what they were, but trace polymer A in a polymer B. So we're looking at very low levels. We can see down to around 200 ppm of polymer A in a pure polymer B. So we had to go through a lot of optimization to get there, but definitely something that's feasible. And we're I'm not sure this will be a QC method, but it'll definitely be something we do routinely, maybe in a sort of pseudo QC role. Looking at, we had these pellets of polymer, and just a kind of practical problem as we were looking at the pellets, why there's circular pellets and cylindrical pellets? These don't look alike. What are they? So we use the Benchtop NMR just to quickly screen, dissolve it in a solvent. We could see obvious differences here. Hydrocarbon-like material, 2D kind of confirmed that. Turned out to be some kind of lubricant that was added. Little did we know, and that would have been disastrous for our production. So it was a great find early on in our NMR experience and journey. Another one is we use an oil that is very prone to esterification. And so we've done some experimentation looking at how the oil changes over time. And so you can see these peaks are growing in as they age, and these peaks are going away as it ages. And so we're looking at implementing this in a factory, a 3M factory, to do consistent daily monitoring of the composition of the oil per se. Looking at commercial raw materials. So comparing, right now there's a lot of raw material issues. I'm sure everybody's familiar with this, but if we're using raw material one, source one, and then when they say we can't supply that, we got to go to source two. Well, then what do we know about source two? So this is an isocyanate, just comparing source one in the pink to source two, which is these three other ones. You can see there are some differences, slight differences in isomer ratios. In this case, we took notice. We really didn't have a choice, and we were sort of on guard. We knew there were some differences. As it turned out, it wasn't a problem in our operation, but we wanted to get out in front of that. So NMR was a real quick, easy tool for us to do this analysis and see any differences that might be there. Quantitating, methylamine in water was another rather simple one, 0.226. A sample that walks in the door and they say, how much methylamine is here? Like I said, very practical kind of environment we live in where people are bringing up real practical problems. And the Benchtop has been a great tool to get us that quick information. There's a lot to learn. I still want to know more of that black box and all those different modes. So when it walks in, I can, when these samples walk in, I have a better idea what to do. So the good news is, initially I had definitely a fog. I think the fog is definitely starting to lift as we start learning more about it, especially with our expert help from Travis, Eric, and others. That's kind of a quick run through of our experience in the last year. Any questions or observations?
So Chris, I mean, in terms of pain points, we've talked a lot about these pain points. I mean, your audience here is, very, very NMR heavy in terms of understanding that black box. What is the one thing that you would recommend that we consider when we try to help teach non-NMR users about the utility of NMR?
I would say two things. One is this one, the really understanding, there's a lot of PChem and, there's a lot of hardcore stuff going on to generate a signal, and to kind of simplify that down into everyday language. And so we can get on the train with you. I think that's one thing. The other thing would be, is the signal part of it, looking at all this, all these variables and kind of simplifying it down and really trying to figure out where are, when we try to analyze the spectrum, which we did back in organic chemistry for simple stuff, but for the novice, how do we start? What are some approaches to starting to look at this, understand it, how to set up the experiment? I think those are the two main things. Like, how does it work? And then when we get the results, how do we start? Or when we're pursuing results, how do we set up an experiment? And once we get the results, how do we kind of interpret that? Those two pieces, starting simple, I think would be really important. Does that make sense?
Thank you, Chris.
Yep.
Yeah. Victor, you want to pipe in with your questions?
Yeah, I got plenty. So Chris, really enjoyed your talk. You mentioned something about deconvoluting semi-resolved peaks. I'm wondering if you can elaborate a little bit on that.
Yeah, and this, we may need others to pipe in, but when we're trying to quantify, in this case, if you can see my screen, we're trying to quantify polymer A and B, and we're trying to find ways to do this in a really routine methodology, kind of like Adam was talking about. So how do we deal with this baseline? And so this craft tool that Chris has, and there may be others, that allows us to kind of extract out, even though the peak is kind of buried, we mathematically are able to extract out that peak. So then we can get our hands on it and quantify it. We can do that if we're good at integration. We've done this. Eric at 3M has helped me with trying to extract this information, setting the baseline, but I'm not going to hand that over to 12 QC operators.
Right.
And automating that is difficult. So that's what we're trying to find as a tool, because benchtop NMR is, we're going to have our peaks are going to be broader. So we're going to run into this more often. So how can we find tool sets that allow us to extract that information and automate that? That's kind of what we're after. I'm not sure I explained that very well. But.
No, that's perfect. And you actually kind of addressed my other question, and that was on how much automation you've been able to incorporate with the benchtop system. But it seems like you've already had that in mind.
We have it in mind. We're talking to a couple of vendors that have systems that try to automate when you're trying to dissolve. It sounds simple, but hand it over to 12 different people, we're going to have a lot of variability. So, and also the safety concerns, depending on what solvent we're using. So we are trying to figure out ways to automate that so that we can reduce the variability. There are systems out there. Right now it's sort of not been handed over completely, but yeah, that's something we're thinking about to make sure that it's a robust tool.
Sure.
Thanks
Best of luck.
Thank you.
Thank you. Good question, Victor. Excellent. Well, thank you so much, Chris. Very good talk. Mark.
Can you hear me?
Yes, we can hear you. Let's try. Sorry, we jumped ahead. So let's keep going on your stuff.
Today I'm going to talk about some of the work that we've been performing here at Takeda, which is to bring the power of NMR to the fume hood where the chemists work, rather than have the chemists have to work at the next to the NMR magnet. And this has been made possible, of course, with the recent miniaturization of NMR magnets. And I'll go through a couple of quick applications that we have, which is inline monitoring at Takeda. One which is just using real-time concentration measurements as a process trigger. And the second example is using NMR to train more typical process analytical technologies, such as flow IR. And then a quick slide on where we plan to go next, or some of the work that we are also doing as well. So next slide, please. So why are we interested? So actually, there was an animation here, but never mind. So why are we interested in NMR's process analytical technology? Well, A few years ago, the FDA came out with this quality by design memo, which basically states quality cannot be tested into products. It should be built in by design. And what they mean by that is, in typical pharmaceutical, at least, and probably in fine chemical synthesis as well, you'll typically charge your reaction vessel with a bunch of reagents, let the reagents rip. At a certain time that you're sure that your reaction's finished, you'll start taking out samples and looking for the yield and purity and all that sort of stuff. The trouble with doing that is, of course, you don't know what happened if, say, your yield's unexpectedly low, or you have a whole bunch of new impurities. You don't know what happened during that time. What went wrong? What kind of environmental, what kind of physical things set the reaction down this wrong pathway? And the idea is, if you're constantly monitoring these kind of reactions, you have a tighter control on what's going on. You might take some mitigating steps, and you also have a better idea of the mechanistics behind your reaction as well. That's not to say that's not already done. There is flow IR, which is used to monitor the functional groups over time, but you can imagine that could be a bit of a mess. You get flow IR is very information rich, but it's also very difficult to tease out which one of those hundreds of peaks are important. Raman is used for the integrity of raw materials, and you can use Beer's law to get concentration, things like that. But one technology that's conspicuous by its absence is, of course, NMR. And I don't think I have to tell everybody here, but NMR provides an atomic resolution picture of the molecules in solution. Every molecule, providing they don't have a degenerate chemical shift, every atom will give you an individual peak within reason, of course. And probably the most powerful thing is the fact that NMR is quantitative and it's a universal detector. So, one proton will always integrate to one proton regardless of what it's attached to, the size of the molecule it's in, providing you acquire the data quantitatively. The next slide, please. So why isn't it used more as a PET? Well, the reason is we basically have two immovable objects, right? You have the huge superconducting magnet. Ours isn't as spectacular as that, unfortunately, but and then you have your chemist working in a clean room or in a fume hood or some other area, which is usually not right next to a high field instrument. So somehow you've got to connect these two information streams together. Next slide, please. And this is possible for at Takeda. We do the kind of reaction monitoring both at high field and low field. And we use a thing called Insight MR from Bruker, which provides a temperature-controlled pathway between the reaction vessel and, say, the high field instrument. It's difficult to see on this is a Bruker Fourier that we have. In this example, you can see the portable, in quotation marks, fume hood that is also a possibility as well. So I'm pointing at the screen. Of course, it's not making any difference. The line will go from the portable fume hood to the high field, or we could wheel up the benchtop next to the fume hood. This could also be a regular static fume hood, of course, and push the benchtop right next to that. So most of the time, the chemists don't have the luxury of having a portable fume hood, of course. So using benchtop is kind of the way to go for us for the kind of work that we're interested in. We got the next slide. Of course, there has to be kind of a paradigm shift between working for high field and low field. There's a cost benefit of analysis you have to do. Of course, you have a much smaller magnet, but it's more portable. And you need to have some realistic expectations. Of course, you're trading portability for less chemical resolution and sensitivity. But if you're doing a reaction mixture, you might have probably molar concentrations of reactant, so sensitivity is not so important. Also, to get good spectra, you typically don't need to have it locked to benchtop fields. Temperature control could be an issue, but inside Bruker has a variable temperature magnet. Our analysis doesn't, but you can use these benchtops in a fume hood, and we've been using it to get preliminary reaction data to do modeling. We also used it again for a stop-go decision, and it could be coupled together with other mobile technologies like flow IR. So we go to the next slide. This is just a couple of the benchtop instruments that we have at Takeda. Right at the very back of that fume hood, you can barely see it behind the yellow balloon, is our Analysis 60 Pro. We recently got it back. It was originally proton carbon. Now it's all souped up with proton, fluorine, and phosphorus because they're more useful at benchtop frequencies. It has the footprint of a large PC. It's 55 pounds, 22 kilograms, which I could, pretty big guy, I could lift that, and you could put it right into the fume hood where the chemist actually works. The Fourier 80 is this proton carbon. That has the footprint of an HPLC. It's pretty chunky though. It's like 208 pounds. I can't lift that up. It took a couple of big burly facilities guys to move that on top of that bench, but we can put it on the bench and wheel it up next to a fume hood or into a clean room. The advantage of the Bruker is, of course, is gradients and temperature control, and having gradients there means you could do basically any 2D experiment that you could do at high field. Proton carbon, you can do that at low field as well. So next slide, please. So I'll just go through a couple of cases that we've used it for. The first one is a simple stop code decision. And we were approached by our process chemistry people. They had a problem where they were performing this distillation, which is to drive off methanol to push this equilibrium from a hemiacetal species to a aldehyde species. The trouble is that had to be done in a clean room, and they would only know they'd only know that the criteria had been met by doing some QNMR. But the trouble is, of course, it's in a clean room. You have to, go inside the clean room, take a sample, disrobe, take your sample out of the clean room, take it into another lab, dissolve it, the sample in some lock solvent, and then transfer it into an NMR tube, then go into the NMR lab, which sometimes is in another building. Then acquire your QNMR data, walk back to your lab, measure the integrals of the two peaks you're interested in, and God forbid you did all that and you didn't meet those criteria, you'd have to go in and repeat this all again. So they approached us to see if there's any way that we could use the benchtop NMR to measure the concentrations in real time. And you go to the next slide. And this is kind of the plot that we got. So I say the data, the spectra are kind of broad compared to what you get at high field, but the data is just good enough for what they need to do. The integrals were, the spectra were required, and the integrals were taken in real time, and then we use a little LabVIEW script to kind of measure the integrals as they came off, and then this was converted into a ratio, and when the ratio met the criteria that the chemists liked, it would actually stop the pump, stop the heater, and send an email to the chemist to tell them that they can go and collect their sample now. The next slide, please. And so this was eventually used in a kilogram scale production. This is a picture inside the clean room with the analysis just pushed up in a little cart right next to it. And this is kind of the little script that was running the LabVIEW schematic, telling measuring the integrals as it came off the line. So we go to the next one, please. This is a second example. This is for monitoring a Grignard reagent synthesis and coupling. Sorry, I'm going to try and move the little thing to the bottom here so I can see the whole slide. There we go. And again, we're going to use the benchtop NMR to measure in real time the concentrations of the Grignard reagent synthesis and also the coupling. If you go to the next slide, please. Again, the benchtop was approached both because they wanted some mechanistic insight, and also, again, to reduce some of the labor that's involved in doing some of the analysis. You can imagine you're doing this multiple times over the course of the reaction, where they'd have to take an aliquot out of the reaction vessel when you assumed it had gone to completion. They'd have to quench it to get ethyl benzene. Then they'd have to dope it with some deuterated solvent, add an internal NMR standard, and then perform QNMR. Again, they would rather not have to do that and just measure the concentrations as the reaction was continuing. Go to the next slide, please. Oh, yeah. So this is just a waterfall plot of one of the first reactions that we ran, where you could see, God, this is going to be difficult, around, you can see the, well, basically, if you look at C1, about 4.6 ppm, you'll see the benzyl chloride's added in with a syringe pump. So that's why the concentration's kind of slowly increasing and then being consumed. At the same time, the Grignard's being, the Grignard is being at around about 6.75 ppm is being produced and then consumed as we add the BPO in there, and we're getting the coupling agent, which the coupling product, which is BP-HP. We can also see the two most common side products, which is dibenzyl and toluene as well, which is good. Unusually, we have a little dichloromethane. NMR doesn't really need to be calibrated, but you need to at least do it once so you know what the response is versus the concentration. And the only thing we could think of and that wouldn't react with the Grignard was dichloromethane. But the thing is, we only have to pump it in once for one spectra. And once we have the electronic measurement of the integral, providing any future experiments are acquired in the same method, we can then electronically compare the integral to this dichloromethane standard that we added in the very first reaction. We go to the next slide, please. This is just the waterfall plot converted into concentration, and this is basically showing the same thing again, where you can see the Grignard in yellow is being, sorry, the dibenzyl, the benzyl chloride is being, the Grignard is being, is increasing concentration, and then you can see it being consumed as once we add BPO. So this is basically telling the chemists everything they need to know. They know the concentrations at different points of the reaction vessel. But one thing, if you go to the next slide, this is just measuring the dichloromethane internal standard, and how we're, sorry, I jumped ahead a slide, how we use this for future experiments to measure the concentrations electronically. So we just jump to the next slide. I can go for that. So while we were doing this, a company called Analytical, which is run by Brian Marquez, we're doing a similar study at Highfield. And you can see, of course, they have much nicer, sharper lines, but we could basically see everything that those guys could see at 60 megahertz, which they were reserving at 400 megahertz. So that was nice. So next slide, please. So one thing is, if you're thinking about taking this to a CMO, is the CMO is unlikely to have a benchtop NMR, but they're going to have a flow IR. But again, the thing with flow IR is you get a whole bunch of peaks. The trouble is you don't know which peaks are referred to, whether your reactants or products, which ones you should be following. But the nice thing is we have this NMR data. So we could then use the NMR concentration profiles to train the IR data. And then once we have the IR data trained, we could more or less forget about the NMR and just go, and if this is a technology transfer, we could then take this to a CMO and they could just use their infrared and tell them which wave numbers to look at. And if you go to the next slide, please, this is kind of what we were observing here. So we basically used these concentration profiles to train the infrared, and we could then tease out which infrared signals that we need to look at. If we go to the next slide, please. Again, we're always interested in dealing with miniaturized versions of these big unwieldy pieces of equipment we normally deal with. We'd love to get this. We have a mobile DART system by IonSense. You can see this guy's taking his NMR spectrometer out in a nice walk around Saugus, Massachusetts here. And this is kind of what spurred a lot of this thing, is seeing this picture and thinking that could we do this with the NMR? The goal would be having the flow IR, mass spec, and NMR all in the same cart, and you can just push it up to the chemist fume hood and plug it in, and off you go. I was really glad to see and really interested in the previous talks mentioning relaxometry. It's pretty new for us. We just recently got hold of this R&D version of the waveguide, and it's been kind of fun to play around with it. I haven't had much luck so far with water NMR. It seems, in my hands at least, it seems to be kind of jumping all over the place. I'd be interested to speak to some of the previous speakers about their experiences with trying to get water NMR working, because we were interested in batch to batch equivalency and aggregation, things like that. And then recently, one of our other groups just gave a presentation a couple of days ago, and they were using this handheld Raman, which I kind of want to get my hands on now too. And next slide, please, which is the last slide. This is just some other things we're interested in. A lot of the molecules we work with are kind of RNA type molecules. So we want to use fluorine and phosphorus to monitor those reactions at benchtop fields as well. So it's kind of nice that we have the analysis modified to do that now. The bane of low field, of course, is the resolution and the line width. So we've been kind of playing with craft. Unfortunately, the application, we tried to get running on the Bruker and they weren't supporting it anymore. So we might have to help Chris about that. Really interested in the sharper thing, which is supposed to help with signal and homogeneity at low field. We'd love to get that going. And then also using, quantum mechanic modeling to get signal integration. As we have gradients on the Bruker, we're kind of playing around with getting ultrafast and NOAA experiments, working on that, because again, not very sensitive, but we have lots of material in there. And again, regular things like QNMR, we're looking at silicon oil polymerization, batch equivalency, aggregation and forensics using the waveguide. In fact, Takeda uses waveguide out in the field right now for as a forensics investigation tool for a couple of projects. And this remains me to thank in the last slide. I'd like to thank William Lee, who did a lot of the analysis benchtop work, and Howley, who's been working a lot with our Bruker F80, really getting up to speed and producing lots of great data now on that instrument. The guys at Analysis were really great feedback, and also we're kind of to modify the spectrometer for us. And we've had some help with Mark Dixon in analyzing the data, which is also one of the toughest parts. And Matteo and Clemens at Bruker, who are helping us with the Fourier 80 and getting that up and running for us. All right, thanks very much. Sorry about the technical difficulties, and it's probably been a little disjointed now, but hopefully it wasn't too terrible. I'm sorry.
Not a problem, Mark. Thank you
and
so
my
much.
accent, I'm sure my accent came roaring back during that.
Very nice, Mark. Thank you so very much. At this time, just want to open up the floor to questions. We got a few minutes left.
No questions. Good.
Feel free to unmute yourself and ask questions. I see some new questions in the chat.
I think there was one from Goncalo.
Yeah, I was just wondering how easy was it to integrate an analysis magnet with LabVIEW I suppose that you have some sort of feedback that triggers the measurement versus at a certain point.
Yeah, it wasn't easy. LabVIEW is a big, learning curve. Luckily, we had a WizKid co-op student who could just sit down and be at one with the computer and manage to get it to work. But it wasn't trivial. It took a lot of finagling to get it to work.
Yeah, that's what I thought. I heard that using Python to kind of make those kind of magnet communicating with a computer, for example, for analysis for inline PAT kind of system is easier. So I was just curious about the experience.
If you're handy with Python, I wouldn't touch LabVIEW.
All right, thank you.
Anyone else?
No,
Well, with that, before I hand it back to Krish, or I don't know if Dave, the name escapes me at the moment. I certainly want to thank Mark, Adam, Greg, and Chris for some exceptional talks. Spread the word. This will be recorded and shared on the Ivan NMR website, hopefully soon. And Eric will update that as soon as possible. With that, I want to again thank the speakers, thank all the attendees, and hand it back to Krish.
Thank you, Travis. I mean, yet another really interesting application in Benchtop, and I'm becoming a big fan of Benchtop NMR these days. Thank you. It's all your work. And so Travis and the team, thank you very much for your participation today. And I don't know if Dave Rice is here or not, but on his behalf, he's usually our MC. On his behalf, I adjourn this meeting. Thank you, and look forward to the next meeting, which is scheduled December 1st. Look forward to the announcement coming by email. Thank you.
All right. Have a great day. Bye-bye.
Bye.